Good afternoon. My name is Arie Bregman, and welcome to our webinar today, which is entitled Understanding Check Valves, Sizing for the Application, Not Just the Line Size. We're going to be covering this topic today by starting with an overview of the many types and styles of check valves. There's more than one, and so you want to know all the different styles that are available to you. We're going to follow that up with some background information on piping design and a little bit of information on flow sizing of valves. We're not going to get into the laborious details of sizing gases and sizing steam and all those. I'm just going to give you a high altitude pass over all of that. But it's important background information to have. Finally, we're going to get into the real subject matter here, which is the importance of sizing check valves, why that's important to you, and what are the benefits to you. I think you're going to find the next 40 to 45 minutes to be very interesting and beneficial. So let's get started. As I promised you just a few seconds ago, we're going to begin with an overview, and then we're going to use that as our stepping off point to go further into the details of the importance of sizing check valves. Okay, so what is a check valve? That sounds pretty simple, and it is. I mean, you've got them in your home. Every piping system in every industry in the world has them. But a check valve allows fluids to flow in only one direction. It prevents backflow, prevents siphoning, protects other equipment like pumps, turbines, tanks. It separates media streams, keeping compounds from backflowing into one another, and usually that's associated with a header or a T. The most important thing to remember here is that all check valves are unidirectional flow control valves that are actuated by the fluid stream. Now, I'm not trying to oversell what a check valve is and what it does. I'm trying to drive home a point that you cannot take the function that the check valve performs for granted. It's a serious thing and requires some serious thought to make sure you've got the right valve in the right application. I'm only going to be showing you a few configuration possibilities on this slide, but there's many possibilities in terms of what they look like. You'll see them with these globe-style bodies that are kind of bulbous in the middle. They've got parallel ends sometimes, or they've got angled type bodies, which is a 90-degree style like I'm showing in the lower right-hand corner here. You'll see them with one-piece bodies, two-piece bodies. You'll see them with top entry flanges where you can get access to the internal parts. You'll see them with a Y pattern body, like I'm showing this Y pattern piston check. That Y is sometimes also straightened out a little bit to give it more of a T pattern shape or a top entry shape. The point I'm making here is that check valves, unlike so many other types of valves like ball valves or butterflies, have a very broad spectrum of shapes, styles, and configurations. And you need to be aware of what they look like because you might have them and not even know that you have them hidden in your system. Now, if your head's starting to spin a little bit just thinking about all those different types of configurations I just mentioned, just wait until you start looking at all these valves and the way they mount into the fluid piping systems. There's all kinds of different end connections. The most common is the flanged raised face end. It looks like a regular piping flange that's somehow grafted onto the end of the body. You'll see that in the lower right-hand corner. There's a ring-type joint, which is a variation of the raised face flange using a different type of gasket altogether. You've got valve bodies that are commonly called wafer style or flangeless style. They're kind of sandwiched in between the pipe flanges, and so they don't have a distinct flange on the body themselves. I'm showing that in that wafer style picture that you're looking at. But then there's other kinds of configurations, butt weld ends, socket weld ends. That's for welding the valve into the piping system directly. There's screwed end. Those are typically smaller valves, but they're threaded onto the pipe, and they've got that tapered pipe thread, female pipe thread into the body. There's sanitary ends. You'll find that in the food, beverage, and dairy industries. Might even find them in pharmaceuticals. There's what's known as a tube flared end, which is for putting these onto smaller, maybe 1 inch or 1.5 inches and smaller type sizes, or that type of piping is called tubing. So we've got numerous different body configurations and even more types of end connections, and you can mix and match them all day long. Well, if I haven't confused you enough already, there are a whole host of different ways that have been developed to accomplish the task that check valves are called upon to perform. We have swing checks, sometimes called flapper valves. We've got tilting disc valves. We've got double door, also known as double disc valves. We've got ball checks. We've got silent or inline valves, and they go by nozzle style and axial flow. So, again, trying to be as confusing as possible. We've got flange insert types of check valves. We've got piston valves that are sometimes called poppet valves. We've got foot valves. It's just, the multiple names for the same thing just adds to the confusion. But the one thing that check valves are not is a safety relief valve. That's a whole separate, unique style valve, purpose built and tested and certified for the purpose of protecting against system overpressurization. In this case, we're just talking about check valves that a little bit of pressure opens them up, and when that pressure stops, they close. I'm going to get into a little bit more definition of the more common types of these valves in just a second. All right, so let's dive into the details of the first four or so different valve designs that I just mentioned. And we're going to start with the swing check valve. It's probably the oldest design, most common style. I think that you've probably could find pictures of these from some of the ruins of ancient Rome or Pompeii. They literally have been around for that long, thousands of years. Flow opens the valve, and when the flow reverses direction, the valve closes. This can cause water hammer, and that's another subject for another time. But it's important to know that there's really no spring or anything. Only gravity is closing that little flapper that's hanging on that swing arm that you're looking at. And it's either gravity or backflow that are closing the valve. This style of valve that I'm showing here with a bolted bonnet type, this pressure seal bonnet may not apply in this, what I'm about to say, but for the bolted bonnet valve, the disc will swing high enough that you can pass a pig through the valve. And you're wondering, a pig? The little critter with the curly tail and the squishy nose? No, in this case, a pig is a kind of a tool that's used to clean out the inside of piping systems. I think it might be called pigs because they make a squealing sound as they go down the pipeline. But only this style of valve will really allow that pipe cleaning tool called a pig to pass through it. The swing check is generally considered to be inline repairable, and they're generally also manufactured to a face-to-face standard that's called ASME B1610. So it's important to know that information. Okay, now we're looking at a valve that's going to be quite similar to the swing check we were just looking at. It's called a tilting disc check valve. Another very common style. Also shares one of the shortcomings of the swing check in that its orientation is sensitive. Flow up conditions can be limitations, as well as even in horizontal lines, you have to have that bonnet surface pointed upwards as they're shown in the picture. The disc has a counterbalance designed to reduce the cracking pressure in larger sizes, and it does that by counterbalancing the weight of the disc. But again, it's the flow that opens the valve, reverse flow that closes this valve. Again, water hammer is an issue with this style of valve. Gravity is very important in this valve. Again, going back to that orientation I just mentioned. This style valve, though, cannot generally pass the line pig through it because there's some of that counterbalance is going to be hanging in the flow stream, which would cause the pig not to go through. It is generally inline repairable, and the face-to-face standards typically are B1610 face-to-face, so it has that in common with the tilting disc valve. Okay, now we're looking at a dual door, dual plate, double D, all these different names apply, check valve. It's a very common style of check valve. There's a little torsional spring in the middle of that valve that acts like an old, like a spring from an old wooden clothes pin to keep the discs or to close the discs against the flow. Again, flow is going to open the valve. Those springs I just mentioned are going to try to assist in closing the valve. Typically, these valves are very narrow face-to-face, and they're regarded as being low cost, very compact design. They're difficult to get tight shut off with because of the those that plate that's splitting in the middle. You've got a very difficult shape to try and seal fluid against. But the face-to-face standard for these valves is typically an API 594 face-to-face standard. Again, low cost and might be a valve to consider in applications where you've got tight spaces and maybe dealing with high alloys. That a big heavy valve is big and expensive. They're not an uncommon valve at all. You'll find them in a lot of applications. I'm only going to cover the four major styles of check valves that you have to choose from. But I did want to save the best style for last, and those, of course, are the products that DFT makes. But these are the silent check valve, also known as inline, axial flow, and nozzle style. They're a relatively new style of valves, and by that I mean they've been around maybe 60 or 70 years, as opposed to thousands. And like all check valves, the flow opens the valve. But there's a significant internal spring, robust internal spring, that assists in closing the valve before the flow reverses, and this is critical to reduce or eliminate water hammer. The style of the valve, because the flow is staying along the axis of the pipeline, tends to reduce turbulence. Typically, these are very robust and reliable designs, and there's a broad range of applications possible with these products, from cryogenics, which would be minus 320 F or minus 196 Celsius, or extreme elevated temperatures, again with the appropriate materials, 1200 F, 650 Celsius would be possible. Even exotic alloys and a variety of face-to-face standards also. The B1610 standard, API 594, and MSS SP 126 are all different face-to-face standards that this style of valve is available in. This real significant advantage of this axial flow or nozzle style valve is that it allows modification of the opening travel to achieve a customized flow capacity. And we're going to get into why that's very important in a few slides. Having given you a brief overview of four major styles of check valves, not all check valve designs work equally well in all applications, and you really do have a lot to consider. You got to think about the flow and the flow capacity requirements. Where in the system is this valve going to be installed? What's the orientation of the valve? Again, thinking back to the tilting disc and the swing check valves, will I be able to get that top access cover at the 12 o'clock or vertical up position? May not work. Those styles may not work well in a vertical line. They might work just fine in a horizontal line. If it is a vertical line, is the flow going up or is the flow going down? Those present two very different circumstances. And then, of course, you got to think about the media versus the materials of construction. Will the carbon steel by stainless steel trim work, or do I need something different? Do I need wear-resistant materials or more corrosion-resistant alloys for the body or the trim? And then thinking about what's going through the valve. Will there be solids or whatever that might have to pass through this valve, and will they be able to get through the valve given the design of the internals of the valve? Finally, will the valve design cause water hammer in this application? That is a very real possibility with vertical lines. Water hammer is a whole other subject for another webinar, but the causes need to be considered when thinking about the application and the style of valve that you're going to be choosing. Okay, so let's move on and talk about piping design and valve sizing now. A lot of work goes into designing process piping, and ironically, you have to start that design process before you have all the design parameters fully nailed down. It's truly an iterative process, as well as a process filled with assumptions at the very beginning. But there is a common piping practice that really says that the piping is often oversized to allow for future capacity needs. And when you're in doubt about what those needs might be, you just increase the pipe size one next nominal size up. That has the impact of reducing flow rates, which is good to reduce frictional losses. Friction increases as a square fluid velocity, so if you increase the flow rate by 41%, the friction will double. So going the other direction, if you want to reduce the frictional losses by half, you would want to reduce that flow rate by about 40%. Less pressure loss can result in maybe some capex savings on pumps and compressors. And sometimes, the assumptions that they're making during the piping design process are a worst case scenario, like a loss of coolant condition in a power plant. So it's important to know what's going on in the piping design people's heads at the beginning of the process. The reason why it's important to know what was going on in the piping design people's heads during that iterative design process is that there could be unintended consequences of oversizing the pipe diameter. They could show up in both capital expenditure and operating expenditure changes, increases. All the valves in the system will be larger and therefore more expensive. All the flanges, of course, have gaskets, and bigger gaskets are more expensive than smaller gaskets. And basically, when you bump up the line size by one incremental size, everything is going to go up in cost. But what also might happen is that you're going to wind up with these low velocities having check valves suffering from premature failure. And that's going to be an annual maintenance cost issue going forward. Bigger valves are more expensive to repair than smaller valves, of course. But the premature failure of the check valves is going to add to those annual maintenance costs and add to them significantly. The system is going to lose reliability, and that's going to be important because then the process that they're being used in isn't being fully utilized, and some inefficiencies are associated with that. But of course, we're here to talk about check valves, and the fundamental thing to remember with check valves is that it is the flow that opens and closes the valves, and only the flow. There's a minimum flow rate usually expressed in feet per second that's required to keep the valve open, and below that minimum the valve will close. Minimum opening pressure is also called cracking pressure, but what you're interested in there is the delta P, or the differential pressure through the valve during the time when media is flowing through it. Higher flow rates are required to fully open the valve than the cracking pressure, so you got to think about will this valve just be off the seat, or will it be fully open? And that's, again, the result of calculations. Flow rates that are in between cracking and the full open position can cause wear on the moving components of the valve, and of course, eventually wear is going to lead to component and valve failure. So I'm going to be using these two terms extensively in the next few slides. That's flow rate, which is typically a velocity type of unit, feet per second, meters per second, or it could be feet per minute rates as well. And then the other term will be delta P, or differential pressure through the valve. And those would be expressed in units of PSI, or megapascals, or kilograms per square centimeter. So jot those down because they're going to be popping up regularly in the next couple of slides. All right, well, all valves have a coefficient, or CV, that describes the ability of the media to pass through the valve. It is a value that has no dimension, but it's related roughly to the flow of water in gallons per minute at 70 degrees Fahrenheit flowing through a valve with a 1 psi, or pound per square inch, differential pressure. And if you're doing all your work in SI units, then you might be looking at a KV number, which is the valve characteristic, as opposed to a CV. So you might, because I just described, that this CV is related to the flow of water in gallons per minute, you might be tempted to think that it has units like gallons per minute per PSI, but it really doesn't. It's just a coefficient that plugs into the sizing equations you're going to see in just a few minutes. All right, well, before I start throwing around formulas and a lot of math, let's understand the three basic types of valves in terms of function that exist in a process piping system. And valves are plugged into piping systems to accomplish three different purposes, basically. One is on-off flow control. Now, those could be manual gate valves, they could be automated quarter turn valves, they could be solenoid valves. but all they do is they turn the flow on or shut it off. Then there's the modulating or proportional flow control products. Those are sometimes globe valves. They could be it could be a quarter turn valve with a positioner on it, but there's a lot of ways that you try to regulate the flow rate through the valve by partially opening or partially closing the valve. And then finally, there's a unidirectional flow control valve. And this is the category that a check valve falls into. And while the check valve operates basically in an on-off kind of a operational mode, you really need to think of them more as a flow-operated unidirectional flow control device. Now, I'm not trying to oversell what check valves are, but you can't afford just to take the check valves for granted either. So let's dive a little deeper into all this. So we'll start with the first of these three basic categories, the on-off flow control valve application. The valve size is selected generally based on the line size. It's the easiest and smartest way to do that. Various types of valves are compared and pressure loss calculations are performed to determine the valve style that's going to produce the minimal amount of pressure loss in the system. And generally, higher CV values or higher valve flow coefficients are usually better for this type of service. Other considerations must also be made for speed of operation in emergency situations, maybe a fast opening or fast closing for emergency venting or emergency shutdown of a system. And that would probably dictate that the valve should be automated. And if that's the case, if I'm maybe shutting down a section of pipe, do I need to consider block and bleed in that section of pipe? And finally, is automating the valve really necessary, or can I get by with a manual or lever operator? Maybe it's a little bit bigger valve, so a gear operator might be worth considering as opposed to the additional costs of automation. So there's all sorts of considerations that are important here, but from a flow sizing point of view, for these on-off flow control, higher CV values are better than lower because you're going to be minimizing your pressure losses with that kind of a situation. Okay, so now let's take this up another level and talk about what's important for sizing considerations for modulating and proportional flow control. Pretty much the desired flow rates or the upstream and downstream pressures are known entities, known values in this kind of an application. And in every circumstance, there's going to be maximum, minimum, and normal flow conditions. And so a desired CV range is developed from all that information. The control valve then is selected from that maximum calculated CV. And basically looking at your different options for control valves, you pick that control valve that gives you that maximum CV at about 80% of that control valve's maximum CV. And again, let me repeat that. So the control valve CV is going to be greater than the CV, maximum CV that you're calculating for your flow conditions. And that margin is about 80% of the maximum of the control valve CV. No control valve does a great job in the extremes of its control range, either the top end or the bottom end, and manufacturers might give you different capabilities of their particular design. But if you think 20% is a min to 80% is a max and try and size your control valves within that 20 to 80 band of the maximum CV, it's generally a pretty safe guideline to work with. So again, selecting a control valve that fits this sizing need is always very critical, and you're looking for a valve that has a CV that's greater than what you're looking for. All right, so let's talk about the sizing considerations for check valves, or the unidirectional flow control valve. Again, the sizing is every bit as critical as the sizing for control valves because, again, it's the flow that opens and closes the valve. And since it is the flow that opens and closes the valve, the flow rates have to be calculated for the min, the max, and the normal flow conditions. These flow rates are often expressed in feet per second or meters per second type of units. And if you know the check valve CV, you should also calculate the delta P through the valve knowing the volumetric flow rate, and compare that to the manufacturer's stated cracking pressure. But in summary, the check valve CV that you're going to install should be less than that calculated or desired C sub V that you've basically put together based on ideal conditions and a perfect world scenario. So just putting a 6-inch check valve into a 6-inch line is going to run the risk of not having enough flow to get the job open, to get the job done of opening and closing the valve. Okay, so I've set the table. Now let's get into the details of the importance of sizing check valves. All right, well, I'm going to start by giving you some good general guidelines here. Minimum flow rates for check valves, regardless of any of the styles that I've talked about earlier. You want to have at least 7 feet per second as a minimum liquid flow rate to open most check valves. Again, I'll emphasize that's a liquid flow rate. 10 to 12 feet per second is probably required to keep that valve fully open. And also check valves generally, all styles, have cracking pressures of approximately 1/2 of PSI. It's not really an industry standard, but it's pretty much what everyone does in their valve design. But you need to do the sizing calculations. That's absolutely important and shouldn't be overlooked. And if you've decided, for instance, that the best check valve style is, say, a swing style check valve, sorry about that, then consult with the manufacturers that are of interest to you for that particular style of valve. If they're technically sound, they're going to confirm these guidelines and maybe refine them just a little. If they say, oh, you don't need that detail, you should walk away. Because it's an important piece of information that you have right here on this slide. Again, try to keep that half PSI cracking pressure in mind. It may vary a little bit from style to style and even size to size within styles that a manufacturer makes. But 7 feet per second is the absolute minimum you should be working with, and 10 to 12 feet per second is a good liquid flow rate for a good stable condition for a check valve. Well, if I've said it once, I've probably said it 100 times already, that with check valves, line size does not automatically give you the valve size. There are specific engineering formulas I'm going to show you starting in the next slide. And the formulas for the liquid sizing are going to be very different from the sizing calculations or sizing formulas that you need for gases or steam. And as far as that goes, there's multi-phase flow and all that, where you have maybe gases with some entrained liquids in them, steam with water droplets, that kind of thing. It all gets into the compressibility of the fluid, and of course liquid is generally considered to be an incompressible. I'm going to keep things as simple as possible right now. We're just going to look at liquid sizing. Liquids are considered to be incompressible fluids, and so the only thing you really need to know about the fluid itself is a specific gravity, which is the density of that fluid relative to water. But you're looking at the sizing calculation or sizing equations here for liquids, and it's the same calculation. I've just expressed it 2 different ways. If you want to calculate the C sub V, which is, again, is the valve design and manufacturer specific flow characteristic, then you're going to use the flow rate Q times the square root of the specific gravity divided by the delta P of the valve, or the delta pressure differential through the valve. If you want to turn this equation around a little bit, then you can solve for the delta P, or pressure loss, by taking the CV divided by the flow rate quantity squared and divide that by the specific gravity. There's lots of handbooks available for this. A good one is the Crane Technical Paper 410. It gives you a lot of background information, but basically these are this one equation that you're looking at is the liquid sizing equation. As I said a few minutes ago in a previous slide, most check valves crack open at about 1/2 PSI. So if you're solving for delta P, you should be looking to have a 0.75 or 1 PSI type of a pressure loss through the valve. If you want to work that the other way around and maybe find out what your maximum CV is, then and put in your maximum desired pressure loss. Let's say it's 1 PSI because it's a nice easy number to work with. And based on that, you can figure out what your check valve specification is going to be in terms of flow coefficient for your application. I'm not going to ignore the gases and steam situations at all. I'll give you a few words about it here. And that is that sizing for steam is normally done using mass flow units, pounds per hour kind of units, whereas gases, you can do that sizing with volumetric, like cubic feet per minute type units, or mass flow units, either one. In addition to the valve-specific flow coefficient that you're looking for, the terminal pressure drop must be known, which is also valve geometry dependent, and a bit of information that you need to get from the valve manufacturer. The formulas themselves are quite complex, and the whole subject matter of valve sizing for compressible media really is a separate topic all by itself, and it's not my intent to give you in this 1-hour course on check valve sizing everything you might want to know about sizing valves totally. That's probably better done in a one-day seminar, or maybe even a college semester type course. But suffice it to say that you're looking at a far more complex situation, because you have to take into account the compressibility of the gases at the temperatures and pressures that you're dealing with. Well, let me begin the summary process of all this. You've done all the math. What are you really looking for anyway? And regardless if these are on-off, modulating, control type valves, or check valves, you always want to match the valves to the flow that's going through them. And check valves, flow rates of 7 feet per second is a minimum. And again, you can convert that to metric units if you like, if you're more comfortable with that. And probably as a max end, maybe 15 feet per second would be a flow rate that where you might start to encounter noise. From a delta P perspective, a half PSI is pretty much a firm bottom end value, but the top end is maybe, again, a little bit squishy and soft based on noise issues and cavitation of the fluid and those kinds of considerations. So you've heard my mantra by now at least a dozen times that all check valves must be sized. You know, the CV required can be calculated if you know the delta P. The delta P can be calculated if you only know the flow through the valve and have an idea of what the characteristics of that valve are. There's problems, of course, with premature wear of valve, component failure, those kinds of things, with either low flow or high flow conditions. So let me get a little bit more specific on what those problems might be. So what happens if the valve CV is too low for the specific application? Well, the flow velocities are going to be high through the valve, and that's going to lead to erosive wear of the internal components. Maintenance costs can increase dramatically because of valve component wear. Component failures within the valve may damage other downstream equipment, and that needs to be considered. Along with the high flow rate, you've got high pressure losses through the valve, and that's going to create vibration and noise that could be a problem all by itself. And so if you have noisy valves or a pipe that's vibrating, you might very well have a high flow condition that you need to look into. If you have what sounds like rocks going through the pipe, then you have cavitation going on. If you have small rocks, you've got a small problem. If you've got big rocks, you got a big problem. But that sound of like somebody dropping rocks on the pipe itself is an indication, a very solid indication that you've got fluid cavitation going on inside the valve. At the other end of the spectrum, you've got problems with valves that have where the CV of the valve is too high for the application, which means that you have very low fluid velocities through the valve, and the valve may be unstable or chattering. Again, maintenance costs can increase dramatically because of valve component wear. If those valve components fail and leave the valve, they can travel downstream and impact something else further down line. I've seen discs wedged in the first 90-degree elbow that was downstream of the valve. And if you have an extreme condition to consider that by itself might be forcing 2 times your normal flow rate through the valve, like an emergency situation where you've got to put extra water through that valve, then the lower normal condition may be causing you problems with your check valves. And that's something that you need to be concerned about. If you hear this tap, tap, tap of an installed swing check valve. It's telling you that you've got a low flow rate and that disc is just swinging back and forth in this low flow condition, and it's going to wear out the hinge pin where that is pivoting from. And that disc could then, that pin fails, that disc can go downstream with the fluid flow in a worst case scenario and either hit the next valve or flow meter or get wedged into the first 90-degree elbow, and you're going to have a difficult time fixing that problem and getting the components out and fixing all the consequential damage that occurs. Well, I hope I've given you a lot of good information to consider, but haven't overwhelmed you. At this time, I'll be happy to answer any questions that you have.
Okay, Arie, thank you so much for that informative presentation. Now we're going to get to some questions from the attendees, but before we do, I would like to remind everyone if we don't get to your question, don't worry. We'll have an answer for you after the webinar. The complete Q&A transcript, including answers we don't have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Okay, let's get to those questions, shall we? The first question asks, since valve CV is proportional to pressure loss, then a high CV in a check valve is desirable to minimize pressure losses, right?
Well, no, that's actually not good, or that's not true at all. It's not a good assumption to be making. Again, you've got to maintain that minimum flow rate of 7 feet per second to open the valve and 10 to 12 feet per second to keep it in the full open and stable position. And that's really what you're shooting for, wanting to make sure that your CV is the valve, for the valve that you're choosing, the CV of that valve is somewhat less than this desirable optimum CV that you might calculate under ideal conditions.
Okay, thanks for that answer, Arie. Here's another question. What do I gain by spending all this time sizing check valves?
Well, the most important thing that you gain is greatly increased system reliability. It's also going to be possible to reduce your capital costs if you're designing a new system by spending all this time and optimizing your check valves. And it will absolutely be one of the outcomes that system will have reduced maintenance costs during the lifetime of the system. So your cost of ownership of that valve and that system is going to be as low as possible. And that's really what you're after, is the long-term costs of operating that process system. So spend all the time up front, spend all the time trying to figure out the root causes of why some of these installed valves are giving you problems, and the payback is going to be immense. It's not just in what you pay for the valve, it's what you pay to own the valve over the lifetime of that valve.
Okay, thanks very much, Arie, for that answer. Here's the next question. I have a vertical line with flow going up. What valve should I be considering?
Well, that's a very good question, actually. And the only valve that's really going to work in that situation is an inline or silent check valve, also known as the nozzle style check valve. A swing check will work in that application, but it's also going to cause a high level of hydraulic shock or water hammer when the pump shuts down or the flow stops for whatever reason. And all that shock can be avoided with a nozzle style check valve or a DFT silent check valve. It's the ideal valve for that application, and it should be the only valve that you consider there in that circumstance.
Okay, thanks, Arie. Here's another question. I hear the disc hitting the inside stop in this swing check valve in my plant. Should I be concerned?
Well, the answer is yes. You should be very concerned, because that sound is basically the sound of a hammer striking the metal that's inside the valve, and that the hammer is the valve disc, and the metal that's being struck is the mechanical stop that's inside the valve. Over the course of time, that disc stop is going to get peened over and may cause the disc to get hung up, but more likely it's going to cause the hinge pin to wear and cause the disc to shift and no longer align with the seat, causing leakage when the flow stops. And this is all caused by low flow in the piping system. Again, the best solution here is a properly sized DFT check valve. That axial flow design aligns itself quite nicely with adjustments of the travel opening of the valve, and that valve can be sized so that it's a perfect fit and stable in that flow condition.
Okay, Arie, we've got time for a few more questions. Let's take a look. Why not just choose the cheapest check valve I can find? They all leak and then fail in a relatively short amount of time.
Well, the answer is you always get what you pay for. An inexpensive valve that's not properly designed for the flow will not prevent water hammer and may contribute to it, in fact. And you're going to pay for that cheap valve probably 5 times over in higher maintenance costs. The smart move is to invest the money up front for the right valve, sized for that application. And as we went through all these slides, you heard what a lot of those application considerations are. It's absolutely worth investing the time. I think that you want to have the most reliable system that you can, and therefore you want to put the right valves, not necessarily the most expensive, but you want to put the right valves. And if that valve is a little bit more expensive, you're investing in the process, you're investing in the reliability of that process, and it's a good investment to make.
Okay, Arie, here's another question. Reducers are an added expense. Are there any other alternatives?
And the answer is absolutely yes. DFT's check valves, as I've been saying, are uniquely designed to make sizing the valves to the flow a simple and low-cost alternative to modifying the piping system. You should contact your DFT check valve distributor with any of your check valve problems, and we will help you engineer those problems out of the process and bring reliability and reduce maintenance costs back into your world. And it's really I've said it a number of times. What you're after here is the right valve in the right application, and this inline axial flow product is well suited to achieving exactly those goals.
Okay, Arie, that's about all the time we have. We're going to have to wrap up this webinar right there. Thanks for spending some time with all of us today.